Hey, and welcome back to our statistical video lecture series. In this video, I want to talk about time series data. But before we get into the specifics of dealing with time series data, I want to talk a little more generally about different data structures you might encounter in public policy analysis. The first type of data structure that you may encounter is what we call cross-sectional data. Cross-sectional data brings together units of analysis that vary across space. An easy way to think about cross-sectional data is if we were doing an analysis of, let's say, counties in Pennsylvania. Counties in Pennsylvania vary across space, physical space in the state, physical space in the world. That is, no two counties can occupy the same space at the same time, and therefore wouldn't be in the data set more than once. You can think about a data set with students or individual survey respondents in the same way. No two individuals can occupy the same space on the planet or occupy the same space in a study or in a town or in a city. Right? So cross-sectional data looks at different units of analysis that vary across physical geographical space. The second type of data structure you may come across is, of course, time series data. And time series data is different than cross-sectional data, where we generally consider cross-sectional data, all the units are unique in space. With time series data, we're measuring the same individual unit over time. So instead of looking at the geographical space or physical space being different across units of analysis, we're looking at time being different across units of analysis. So in this regard, time series data looks at the same physical space or the same physical person over multiple time periods. This adds several complications because, unlike cross-sectional data, where we can generally assume that units are unique across space, we know that with time series data, the units are not unique because it's the same person or same physical entity at different time periods. Another way of thinking about that is data collected for you at time period 2 is not independent of data collected for you at time period 1, because you are still you between time period 1 and time period 2. That's a little bit different than collecting data, let's say, for the state of Wyoming, which is unique from the state of Pennsylvania at the same time in, let's say, 2019. The final data structure, which adds even more complication, is what we call panel data. And panel data combines cross-sectional data with time series data. So whereas in a single cross-section we have a bunch of individual units measured at the same time, in time series data we have one individual measured at multiple times. In panel data we have multiple individual units measured at multiple times. Panel data is really good at boosting the number of observations, since n would be equal to the number of units you have times the number of time periods, but it adds an additional complication because now you have correlations between observations within clusters. That is, obviously if I measure, let's say, multiple faculty members at multiple times, I'm still me at time period 1, 2, 3, 4. That's very different than being, let's say, Dr. Holoviak, who obviously is going to be correlated within herself, right? So Dr. Holoviak's measures for time period 1, 2, and 3 are going to be correlated with each other, but they're going to be unique from, let's say, the data that's collected for me. So once again, with panel data, you have now clusters of observations where there's intra-cluster correlation because of the time series component for individual observations, and then variation between clusters, that is variation between the observations for each individual entity. So in this particular video, we're going to talk about some of the complexities of dealing with time series data, particularly how trends affect different observations at different points in time, and how we then correct for some of those trending processes, because we know that observations are not uniquely whole from each other at different time periods. So let's jump into some of those specifics and how we tackle some of those specifics in our statistical modeling.
All right, to demonstrate a little bit about time series data, here in Excel I've got some presidential approval ratings for Donald Trump, starting here in the series for January 20th, 2017, kind of the beginning of his term after his 2016 election. So you can see here that I've got essentially the same president. So in this regard, this is not a cross-section, it's just a single president, Donald Trump. And every observation measures the approval and disapproval rating for that single person. So you can see here, on 120 to 122, Donald Trump had an approval rating of 45 and a disapproval rating of 45. The next day, basically on 121 to 123, he had an approval rating of 45 and 46. And these numbers are tracked all the way down through into 2018 in this particular time series data set. Now, as we kind of mentioned before, one of the sort of interesting things about time series data, particularly when we're only looking at a single observation, is that the observations themselves are going to be correlated in what we call serial correlation or autocorrelation, meaning that the observation at, let's say, time point 1 is in many ways influencing the result at time point 2. Sort of substantively for approval ratings, unless something drastic happens, the people that disapprove or approve of Donald Trump on 122 are still going to approve or disapprove of Donald Trump on the next day, 121 or 123. So the challenge of analyzing time series data is we have to take into account that time series data are heavily trended by that underlying factor, that there is a sort of serial correlation or stickiness to the data, meaning that we know that values at time 1, 2, and 3 are probably driving the values at time periods 4, 5, and 6. All right, so to kind of illustrate some of these points, let's look at a line graph of the disapproval rating for our time series. A line graph simply plots each date, which is on the x-axis, and you'll notice these aren't formatted like they are in the data set. These are formatted as integers. It takes each date and it plots the disapproval rating, and then it connects all those dots with a line to show you kind of how the values move over time. So the first thing you'll notice here is that the time series data are really noisy in the sense that there are lots of little spikes and peaks, and you can see how rapidly the data change around sort of the values from day to day. Now, of course, we know that the sort of general level of disapproval ratings are going to be heavily trended through that autocorrelation or serial correlation process. Donald Trump's not going to suddenly become not Donald Trump from one day to the next. Once again, the people that disapprove of him on day 1 aren't suddenly going to approve of him on day 2 in great numbers. So we know there's not going to be a huge change from each time period, but there is some variation between the time periods in the disapproval ratings. Once again, you could take whole classes on time series data. The point here is just to simply kind of mention or kind of showcase that depending on what you want to do or what you want to know would really drive your measure. So if you're really concerned about, let's say, how news stories about Donald Trump every day affect his approval ratings, you might really care then about those rapid peaks and troughs that occur from day to day. So if you were to count, let's say, the number of negative CNN stories that Trump gets on a day, or the number of positive news stories that Fox News gives on Trump a day, you could then attempt to match those values up to the peaks and troughs, really the differences in kind of the average of where Trump is in his approval ratings for a given time period. So there are a lot of different techniques you can use for time series data depending on the questions you want to ask. The only thing I'm really going to showcase in this video is that one useful trick to figure out what the trend is to get rid of the noise is to kind of reproduce a line graph with some kind of smoothing procedure applied to it. So the second figure that I show here is the same data with a Loess smoothing curve. It's a statistical measure to smooth out the peaks and the troughs to give us a better sense of how his approval ratings, or in this case disapproval ratings, have really changed over time. You can see in the smooth graph that disapproval ratings kind of really increased quite heavily over the series, and then actually started to decrease, meaning that fewer people started to disapprove of the way President Trump was handling his job closer into 2018. And, once again, we don't have the tools right now. We're not really going to have the tools in this class to answer questions about why that's happening. But you can almost see in the data that there are these two different time periods, this sort of period of increasing disapproval ratings and this time period of decreasing disapproval ratings. Maybe what you'd want to do is kind of figure out, was there some major event that led to this transition or this change in how the trajectory of disapproval ratings was going? One way you can do that is through what we call interrupted time series analysis. So even though we're not going to deal with a lot of these tools in our class, they do exist to handle the specific challenges and specific questions people might have that utilizes time series data in a meaningful way.